Okay, so we are going to look at the idea of Archimedes' principle and how it relates to floating and sinking. So we need to imagine that we have a fluid container, and we're going to talk about the idea of water, but it could really be any fluid. It doesn't matter what the fluid is, the principle is the same, and the ideas governing it are the same. So let's imagine that we have a container full of fluid, and we'll just say water. And inside that container, we have an object. Now, what I want us to think about is what interactions is that object experiencing? So just like with our analysis of forces, the idea of floating and sinking and the idea of Archimedes' principle comes from our analysis of forces. Okay? So what is this object interacting with? Well, as always, that object is interacting with the Earth. So we know that there's still a force of gravity. We'll just call this the block and the Earth. And we know that that interaction is in the downward direction. So there certainly is a force acting on this block due to the Earth, the mass of the Earth. Well, the block's also interacting with the water. Okay, so we also know that there is the force of the water, and that's between the block and the water. Now, how do we figure out that force? Well, the water is interacting all around the block. It's interacting at the top, it's interacting at the bottom, it's interacting at the sides. And how does that look? How does that interaction look? Well, if we imagine the interaction at the top of the block compared to the bottom of the block, does it look any different? And we need to think about the force acting across the area of that block. Force per area, pressure. Let's think about the pressure as we go deeper and deeper into the water. And if we think about that pressure as we go deeper and deeper into the water, we are going to discover that as we go deeper, the pressure increases. And it actually increases linearly. So let's think about why that might be. Well, we know that pressure was what? Well, pressure, remember, is the force per area. So let's imagine little bits of area throughout this water. And look at how the force might look for those same size pieces. Okay, so our area is going to be constant, and that's going to give us that normalization for the pressure of those pieces at those various points in the water. Okay, well, at this top point, we have all of this water above that small point. And so, of course, water is experiencing the force of gravity. It's massive. And so we have the force of all this water on that area. So we have a pressure value. If I go a little deeper, well, now I have a larger column of water. And I go even deeper, now I have an even larger column of water. So the deeper and deeper I go, the larger the force is acting on that area, the larger the pressure. So as we go deeper in water, and we've had this experience, we increase pressure. Now, is that pressure just above us? Imagine you're doing the dishes, and you put on your rubber glove so that your hands don't get so dried out while you're doing the dishes. And you stick your hand into the tub of water. Do you just feel pressure at one point? Do you just feel a force? No, you feel that glove being pushed against your hand. There's forces on all surfaces of your hand as it's in that water. You can feel that by that glove being pushed against your hand. Your fingers are actually feeling a larger force than the top of your hand because the pressure is greater at the bottom, therefore the force is greater on any area that you're experiencing. So we also want to think about it in a directional standpoint. What direction is that glove being pushed onto your hand by the water? Well, it's hard to imagine the top because the top is open and your arm's hanging out. But you can imagine that if I covered this brick with a plastic bag, that plastic bag would be pushed against that brick from all directions. So from the top, that plastic bag would be pushed in the downward direction. That water is being pushed, is compressing the bag on the top. And there's a small force relative, small force, because there's lower pressure there at the top. At the bottom, and with your fingers in your glove, the glove is being pushed towards your fingers. So at the bottom, the forces are all upwards on that block with a bag around it or on your fingers with the glove. Now, why did I draw those arrows bigger? Well, the pressure is bigger there. We're deeper in the water, so the pressure is bigger. The area is the same if we look at any little standard area, and so the forces must be bigger, okay? All right, well, what about on the sides? Well, the glove is squished towards your hand, right? As a plastic bag around this brick would be squished towards the brick. The forces are inward, and so we have a force in this direction and one on the opposite direction. Now, why am I drawing the arrows bigger? Well, as we go deeper and deeper into the water, the pressure increases, the forces are increasing. We have more water on top, pushing down, therefore the pressure is larger, and therefore the forces are larger. All right, so how do I look at the kind of net force of the water acting on that brick there? Well, we should recognize that any force at the same level on the sides of the brick, well, they're canceling each other out. There's an equal force to the left as there is to the right for any one of those levels as we go down. So those forces cancel each other out. The forces on the top are smaller than the forces on the bottom. So the net force by the water is in the upward direction. So if I was going to draw a free body diagram of this block in the water, I would see that I have the force of gravity in the downward direction and the force of the water, which we call a buoyant force, B, in the upward direction. So the net force by the water we call the buoyant force. And it acts upwards. All right, so the net force by the water is going to be up, or by the fluid, any fluid that we have is going to be up. Now, let's for a minute imagine that we take this exact same block and instead of it being in the middle of this fluid-filled container, we put it at the bottom of the fluid-filled container, but it's not touching the bottom. Okay, so that's important right now. It's not touching the bottom. So again, the only forces acting on this container are the force of gravity and the force of the water. Now, has the force of gravity changed? It's the same object, same mass, and remember, we know that the force of gravity is equal to the mass times g. So the force of gravity on this object has not changed. What about the buoyant force? Has the buoyant force changed? Well, the buoyant force, that's the force due to the water. We know it's going to be in the upward direction. Again, the forces on top are always going to be less than the forces on the bottom because there's more pressure on the bottom than there is on the top. And the forces on the side are always going to be equal because at every level that we move down in the fluid, those forces, that pressure is the same. Those forces then are also the same. So what about the net force? I'm deeper, so my bottom forces are bigger, but so are my top forces. And the difference remains the same. So the buoyant force is upwards, and it's equal to the buoyant force in the middle. So these two buoyant forces are the same. Because even though my forces along the top are bigger, my forces along the bottom are bigger. And we said that the pressure increases linearly. So for every change in pressure I get at the top, I get an equal change in pressure at the bottom on that exact same object. And therefore my buoyant force doesn't change. So once I have a fully submerged object, fully submerged object that is not touching the bottom, because then I'm going to have another interaction, the bottom there, that I have to consider in terms of the net force on the object. And we'll get to that. But for a fully submerged object, the buoyant force remains the same. So let's think about that principle. Now, once it's on the bottom, the buoyant force is also the same, but the net force on the object has changed. So we can generalize that for any fully submerged object, regardless of its depth, the buoyant force stays the same. The net force on the object is what's going to look a little different if it's touching the bottom, because of course we have that interaction. Now, why is this important? Well, it's important when we consider whether an object will sink or float. The buoyant force is related, or is part of the interactions that are going to come into play for sinking and floating. So let's look at how we're going to determine that, and how do we get the buoyant force to begin with? All right, so we'll take those two items independent. First, let's look at where the buoyant force comes from. Well, as I put an object into the water, I want to do this a little differently so I can try to, these markers are dying at the end of the semester. There we go. I'm going to put the water a little bit higher there. Okay. Here are my 4 scenarios as an object is going, that orange marker I'm going to put down, is going deeper and deeper into a fluid. So we start with just a little bit of that fluid, the object within the fluid, and then more of that object is in the fluid, and then completely submerged and completely submerged. And I intended to at least try to draw the fluid levels at different heights. These two are the same. This fluid level is a little higher than this one. Why might I do that? Well, as I put an object into a fluid, that object takes up space. It has a certain volume. And if it's taking up that space, well, it's got to push the fluid out of the way. So it's going to displace the fluid that it's taking up. Well, how much will it displace? Well, it's going to be equal to the volume of the object that is within the fluid. Now, you might know this from cooking, so perhaps if you like to bake, one of the key ingredients in a lot of baked goods is shortening. And shortening is that like buttery stuff, okay? And it comes in a can. Well, now it can come in sticks and you can slice it. But in the old days, it used to come just in a can. And you can still buy it in a can. And you had to measure, let's say, a cup of shortening. And so perhaps you learned in your home economics class that if you take a giant tub of water, let's say you fill a 8-cup Pyrex dish with water, and you fill it all the way to 8 cups, and then you start scooping out the shortening and putting it in the water, well, it starts to raise the water level. And as soon as you raise the water level by 1 cup, well, you have 1 cup of shortening. So that shortening displaces the water in an amount equal to its volume. So as I drew these objects being submerged in the water, I've submerged a little bit of the object, small amount of the object. As I submerge more of the object, my water level increases. I displace more water because more of the object is taking up that space. However, when I go from fully submerged to deeper, well, the same volume is taking up that space, and so the water level will no longer change. Well, this is important And then it has to do with Archimedes' principles specifically. Archimedes discovered that the amount of displaced water was related to the buoyant force. And what he discovered was that the weight of the displaced fluid, is equal to the buoyant force. This is Archimedes' principle. It tells us the weight of the displaced fluid is equal to the buoyant force. Now, does that make sense kind of intuitively of what we've learned about the force, the buoyant force, on an object? If I have an object that's partially submerged, we know that the buoyant force is related to the net force acting on the object, of course, on all sides. And we know that the right and left sides, let's say, are the same. So we only have the force on the bottom. There's no forces on the top because it's not yet fully submerged. As I further submerge the object, well, now my forces are going up. Why? Well, the object is deeper in the water. And again, the rights and lefts cancel each other out. We still don't have anything on the top, but the force is going up. And we know that the amount of displaced fluid is also going up. So it's consistent with our idea of the buoyant force. As I go fully submerged in the water, well, now even more volume is displaced, and so my volume of water or fluid is larger, so I'm going to have a larger weight, and I would expect a larger buoyant force as I fully submerge the object. There's a larger, imagine this right at the very top, the largest difference is now been achieved. As I go further into the water, no more weight is displaced, no more fluid is displaced. Therefore, there's no increase in the weight of the displaced fluid. It's the same amount of fluid displaced, and therefore the buoyant force remains the same regardless of the depth. Consistent with sort of what we talked about from a conceptual idea of buoyant force. So those ideas are consistent. So, like I said, Archimedes discovered this idea. There's a beautiful story about how he was determining whether the king's crown was made of gold. And knowing the density of the king's of gold, he was able to discover that indeed it was a fraud. You can go read about that story. You may have heard inklings to it. It's the famous Eureka story where Archimedes jumps out of the bathtub fully naked, runs through the town and says Eureka, which means I figured it out. And it's a fun little story, but it talks about this idea of the buoyant force and that the buoyant force is equal to the weight of the displaced fluid. So if we're able to weigh how much of that fluid is displaced, we can then determine what the buoyant force on that object is. All right, well, this is going to be very important with looking at whether an object sinks or floats, and that will be in a later mini lecture, a different mini lecture. Archimedes' principle, just the weight of the displaced fluid is equal to the buoyant force. Good job.